Okay, the last section of Chapter 10, Geometric Probability. And go ahead and answer your warm-up questions. Number 1, 36 feet squared. Number 2, you should have 20 meters squared. And number 3, what is the probability that any 3 points chosen randomly are collinear? You know, we're going to talk about this today. And we know that probability is the number of favorable outcomes over the number of possible outcomes, right? And so the favorable outcomes here, you could list. An example would be ABC, or ABD, or even ACD, right? And then you would list the all possible outcomes and what is that ratio equivalent to? 2/10. So today we will calculate geometric probabilities and use them to predict results in real-world situations. Geometric probability. So remember that in probability, the set of all possible outcomes of an experiment is called the sample space. Any set of outcomes is called an event. If every outcome in the sample space is equally likely, then the theoretical probability of an event is the number of outcomes in the event over the number of outcomes in the sample space. Geometric probability is used when an experiment has an infinite number of outcomes. In geometric probability, the probability of an event is based on a ratio of geometric measures such as length or area. The outcomes of an experiment may be points on a segment or in a plane figure. Here are some examples. So we have when it comes to length, an example is this segment AD with points BD. So the sample space is the entire segment AD. An event here would be points on BC. The probability of a point being on BC would be BC over the entire sample space AD. The sample space here in this circle example would be all points on the circle. An event might be all the points in a shaded region of the circle. And the probability of a point being in the shaded region would be the measure of the angle over the entire 360 degrees. All points in this rectangle would be a sample space. An event would be all the points in the shaded triangle. So the probability of a point in the shaded triangle would be area of the triangle over area of the rectangle. If an event has a probability, P, of occurring, then the probability the event is not occurring is 1 minus P. So as an example, we have the probability of flipping a coin, let's say, is 1 out of 2. Flipping a heads on a coin is 1 out of 2. And the probability of not flipping a heads is also 1 out of 2. Let's use length to find geometric probability. A point is chosen randomly on segment PS. Find the probability of the point being on RS. Okay, so we find the points on RS, and they fall on a segment that is 5 units long, right? And the entire length of segment PS is 25, right? So we have 5 to 25, or 1 to 5 when we simplify the probability. How about the point is not on QR? Probability the point is not on QR would be 1 minus the probability that it is on QR, right? So the probability that the point would be on QR is 13 over the entire segment, 13 over 25. And so the probability it's not on QR would be us 13 over 25. And we can make 1 25 over 25, right? And so we have 12 over 25. You could have also, I suppose, added 7 and 5 and placed 12 over 25. Okay, how about the point is on PQ or QR? The probability that the point is on PQ or QR. It's kind of a combined probability, so we say what is the length of PQ and QR together? And that's right, we add them. So we have 7 plus 13, or we have 20, right? 20 over 25, which leaves us with a probability of 4 to 5, right? A pedestrian signal at a crosswalk has the following cycle. Walk for 45 seconds and don't walk for 70 seconds. What is the probability the signal will show walk when you arrive? So to find the probability, we could draw a segment to represent the number of seconds that each signal is on. Walk for 45, don't walk for 70, right? So we can see that we have 45 seconds in favor of walk over the entire 115 seconds of the light cycle, okay? And we can simplify that to 9 over 23, which is approximately 0.39. All right, so if we arrive at the signal 40 times, let me see if I can stretch that, predict how many times you will have to stop and wait more than 40 seconds. So here's a little diagram that I drew. We arrive at a signal, and here's the signal cycle. From A to B we have the walk sign, and from B to C for 70 seconds we have don't walk. So we have to determine how much time, or we need to determine the possibility of waiting more than 40 seconds, right? And we could kind of draw that in. We could start here at B, right, and wait for 40 seconds. And then anything beyond that 40 seconds right there, let me draw on 40, would be waiting more than 40 seconds, right? So this little segment from here, let's label it D. From D to C represents the time that you could spend waiting for more than 40 seconds at the light. And so how many seconds is that? If B to C is 70, then D to C must be 30, right? 30 seconds. So the probability of arriving at the light and waiting for greater than 40 seconds would be 30 over the entire 115, right? And that can be simplified to 6 over 23. So there's your probability. If we arrive at the light 40 times, what is you will probably stop and wait for more than 40 seconds. How many times? And so we simply take the probability we found and we multiply by 40 times. And so we have about approximately 10 times we will wait more than 40 seconds at this light. Okay, so using this information below, what is the probability that the light will not be on red when you arrive? Here's a normal red, green, yellow light. What's the probability it will not be on red? Well, how many seconds is it not on red? We can see 30, right? Out of how many total seconds is the light on? 60. So 1/2 or 0.5, it will not be on red. Let's try a spinner problem using angle measures to find probability. So using the spinner, find the probability of the pointer landing on yellow. So we know the entire circle is how many degrees? That's right, 360. So the probability it will be on yellow is the 140 degrees out of the 360 total possible degrees, right? And then we go ahead and simplify, and we have 7 out of 18 times. Let's find the probability of landing on blue or red. Blue or red, Either one is a combined probability, right? So we can simply add 60 plus 52, and that is 112. And 112 over 360 is a probability of 14/45, 14 out of 45. About the pointer not landing on green. And go ahead, pause, come back and check. And very good. I'm sure you have deducted the green from the total, and that would be 7 out of 10 times not landing on green. Let's use a spinner to find the probability of the pointer landing on red or yellow. Red or yellow. And red or yellow is 80 plus 100. And so that would be half the time, wouldn't it? The probability is half, 1 out of 2, that the spinner will land on red or yellow. Let's find the probability that a point chosen randomly inside this rectangle is in each shape, round to the nearest hundredth. Okay, starting with the circle. What is the probability that a point chosen randomly in this rectangular space is in the circle? So we simply find the area of the circle, right? And that's pi r squared. And the area of the rectangle, which is 50 by 28. So the points in the circle over the entire space gives us this probability, approximately 18/100ths. About the trapezoid, go ahead and find the trapezoid and one of the two squares, and we'll come on back and check your work. So the trapezoid, there it is. You should have found that area, 450 feet squared, and we still have our rectangle. So 450 over 1400 is 32/100ths. In one of the two squares, we simply find the area of 200 feet squared, and place that over the area of the entire space, and we have 14/100ths. Okay, try the lesson quiz and check your work. Point on EG, 3/5. Point not on EF, 13/15. Find the probability that the program will be scanning when you arrive at the computer. This is kind of like our light question, and it's 0.25. And the probability of landing in the shaded area, 95 plus 85 over the 360, or 0.5. And the probability that a point chosen randomly inside the rectangle is in the triangle. So we have area of the triangle over the entire area of the rectangle, which is 48 inches squared. And we have 0.25. Excellent, good job. Have fun.